In this problem, what we want to show is that if a sequence converges pointwise to 0 and they are decreasing, then we don't know whether these functions are Riemann integrable. Therefore, we cannot talk about their Riemann integrable. Okay, but we do have the lower Riemann integrals of these functions. And what's interesting is that the limit of these lower Riemann integrals is equal to 0, knowing that if they are Riemann integrable, then the lower integral is exactly the normal integral. Okay, so we have a sequence. Let Fn be a sequence defined on AB. Okay, and we assume that the Fn's are pointwise convergent to 0. Okay, and that Fn plus 1 is less or equal than Fn. So they are decreasing basically. Obviously, this will imply that 0 is less or equal than Fn for any n. It means that these sequence of functions are in fact positive. Okay? Great. So we are going to try somehow to squeeze in Dini's theorem, and for that we need some continuous functions, and for this we need the following result. So before I proceed, recall the following. Okay, this is very, very interesting, beautiful, in fact, to see what's going on for the functions and how we can approximate them by some kind of continuous functions, such that the not the Riemann integral but the lower Riemann integral is by approximation, in other words. Okay, so let's f be a positive function, and we know that the lower integral, of course, defined on AB, defined on AB, and we know that this one is the supremum of the lower sums, the lower Riemann sums of f with respect to partitions. Okay, and every lower sum is in fact an integral of a simple function. So we can find, because this is the infimum, so we can find, let epsilon be positive, okay, then there exists a simple function defined on AB, okay, such that s of x is less than f of x. Remember, because the lower sums here, the values are given by the infimum. So you can take the infimum on every interval of the partition, okay? Such that the lower integral, okay, of f of x, okay, minus the integral of s, which is basically the lower sum, is going to be less or equal than epsilon. It's greater than 0 and is less than epsilon. Okay? So remember that this is exactly the integral of the simple function. Okay? So in terms of integral, these two functions, f of x and s of x, are very close to each other. Okay? So let us now look at s closely. What happened? Because if I want to use the Dini's fixed point theorem, Dini's theorem, I need to find some continuous functions close by in the sense of the Riemann integral. So here, let us go back to s of x, focus on s of x, okay? So what do we have? We have this partition, okay? And we have the function which is basically constant, positive, okay? My function is positive, f is positive, okay? So here what we do, we come inside, so let me show you exactly how to do it. you come inside every interval. Okay? So you stay, you don't touch, you keep it as is. You go inside, you go to the value that you have in this interval, and you join them. Okay? So you have this function f, and when you go inside basically just little delta. Okay? So this blue function, so basically this is how it looks like. If you go back to your original, so it looks like this. Okay? And here you take it 0, huh? On this little gluing party here. Okay? Okay, so what happened now? Obviously, the blue function, okay, let's call it this function here, this blue function, we'll call it b of x. Okay, so obviously b of x is going to be less than s of x. Okay, so we found the function that is what? Continuous and less than s of x. What's interesting is that if you take the integral of s of x minus b of x, okay, from a to b, so this function will be equal to 0. You see on this common part, okay, here, this common part here, where the blue curve and the red curve they intersect, they are equal. So on that one is equal to 0. So you are basically only left on these small intervals, okay, with length delta. So you can make this less than, less than, and how many do we have? So it's delta, okay, because it's less than delta, okay, the length of these intervals. How many do we have there? We may have, because the partition is very well defined. So S is, the simple function gives us the partition is fixed, okay. We're finding B, the continuous function. So you have B, okay, sorry, not B, delta, the length of each one of them, okay, time how many of them? Let's say n plus 1 or n, okay. It's finite, fixed. Delta is the one that we are playing with, okay? And the function is, since the function s is bounded, so we can have a number m, which is the upper bound for s, okay? So this gives me what? That since delta is can be taken as small as we want, okay? So we can make this very small. Meaning that given it, that epsilon, I can find, so there exists b, a function on AB, such that b of x is less than s of x, okay, less than f of x, such that the integral of f of x minus b of x, okay, will be equal, so this is equal to the integral from a to b of f of x minus s of x dx. Everything is positive, plus or less or equal, to be precise. Okay, from a to b, s of x minus b of x dx. And as you can see, I can make this less than epsilon. So the first one is epsilon, the second one is epsilon, so 2 epsilon. Okay, but if I started with epsilon over 2, then I can have here epsilon. So this tells you that basically you can approximate a function by a continuous function below it, positive function of course, f, by a continuous function f which is still positive, okay, and such that the integral or the Riemann lower integrals uh, are very close to each other between f of x and b of x. Okay? Great. So now let's go back to our problem. So what do we have? We have this sequence of functions, and we want to show now that the fn's are the conclusion is of all this is that the lower integral from a to b of fn of x dx, it goes to 0 as n goes to infinity. Okay, that's what we want to show. So for this, what we are going to do, we're going to have we're going to start by looking at f1. So I know that uh, f1, I will find there exists c1 from ab into r such that c1 of x is less or equal than f1 of x. Okay? Okay. Then I take f2. What do I know? I know that f2 is less than f1. So I'm worried about c1. So I'm not going to take f2, but I take minimum of c1 and f2. Okay? And for this one, I'm going to find c2, okay, from AB to R, such that. Okay, now, how do I pick these functions? Okay, I take the functions such that the integral, okay, of a, b, f of 1 of x minus c1 of x dx is small, less than epsilon. But the problem is, later on, I'm going to have epsilon plus epsilon plus epsilon. This will be a problem. So what I'm going to do is have it over 1, 2. Okay? Good. And now when I get C2, I want C2 such that, so C2 is going to be such that the lower integral from a to b of the minimum of c1 of x f2 of x minus c2 of x dx, this will be less than epsilon over 2 squared. Okay? So by induction, okay, there exists this sequence of Cn of x, continuous functions defined on AB, such that Cn plus 1 of x will be less than minimum of Cn of x and fn plus 1, and the integral from a to b, the lower Riemann integral of the minimum of Cn of x fn plus 1 of x minus Cn plus 1 of x dx less than epsilon over 2n plus 1. Okay? Okay. So let us make some quick remarks, okay? Number one, if you look at C2, let's go piece by piece, okay? So what do we have? We have C2 is less than the C1 of x and f2 of x. So if I take now f2 of x minus c2 of x, this will be less or equal than f is positive, and since c2 is less than the min, okay, minimum of c1 of x, f2 of x, plus the minimum of c1 of x, f2 of x, minus c2 of x. Let us just, I want to say something here. Focus on this piece here. Okay, what happened? If the minimum is f2, then we have f2 of x minus f2 is equal to 0, right? And if the minimum is c1, then we have f2 of x minus c1 of x. But f2 is less than f1. So this will be less than f1 of x minus c1 of x, because this is positive. When this one is equal to 0, the one I mentioned, then this one being positive is going to be bigger. Okay, and f2 is less than f1, then this will be always less than this one. This one here will be always less than the one we have here. Okay, plus the minimum of c1 of x, f2 of x, minus c2 of x. Now these two functions are positive. This will tell us that the integral lower of f2 of x minus c2 of x dx will be less or equal than the integral from a to b f1 of x minus c1 of x dx plus the lower from a to b lower Riemann integral of minimum of c1 of x f2 of x minus c2 of x dx. Okay, so here what happens. So this one will be less than epsilon over 2 plus epsilon over 2 squared. Okay, remember that's how we found this is epsilon over 2 to the power n plus 1, and if you go back, one has epsilon over 2 and the other one has epsilon over 2 squared. So same argument will tell us, in fact, same argument, if I use the same arguments, we will find that this sequence Cn that we build, in fact, it satisfies the following, that Fn of x minus Cn of x, okay, it's going to be less than by epsilon over 2 plus epsilon over 2 squared, epsilon over 2 to the power n plus 1. Okay? And this will give me that is less than, for example, epsilon. That's why I had to divide by 2 to the power something. Okay? So now let us focus on the Cn's. What happened to the Cn's here? So this sequence are all continuous functions. Okay, and Cn plus 1 was chosen to be less than the minimum of Cn of x Fn plus 1. And therefore, the Cn of x, Cn plus 1, is less or equal than Cn of x, and they are all positive. So you have a sequence of continuous functions, okay, which are decreasing, and they are decreasing and they are continuous. And using the facts that, what do we know about our Fn's? They are decreasing, they converge pointwise to 0. So remember that the Cn's are also less than, Cn plus 1 is also less than Fn plus 1. Since the fn's they go pointwise to 0, we know then that Cn of x will converge pointwise to 0 as n goes to infinity. So what do we have? We have a sequence of continuous functions decreasing. They go to 0 pointwise on an interval ab. So Dini's theorem tells us what? That the Cn's, okay, they converge uniformly to 0 by Dini's theorem. Okay? And this will imply that they will imply by Dini's theorem that there exists an n such that the integral, because they are continuous, therefore we have the Riemann integral, and they are positive, dx will be less than epsilon times b minus a, because the functions are all less than epsilon. Okay? So, again, if you look at, for example, which will imply, in fact, that the integral from a to b of fn of x dx will be less than, okay, from a to b fn of x minus cn, because this is positive, plus the integral from a to b cn of x dx. So this one will be less than epsilon. This one will be epsilon times b minus a. So if you choose basically the right epsilons, as usual, you can make this arbitrarily small. Okay? So, which means that the limit of the lower Riemann integrals of the fn of x dx is equal to 0 as n goes to 0, as claimed.